Welcome. In this video, I will be summarizing and critiquing 3 papers on machine learning, as well as describing and critiquing a re-implementation of one of the papers. The first paper in this review is DualGAN, Unsupervised Dual Learning for Image-to-Image Translation. Image-to-image translation is the process of learning how 2 images are related for the purposes of accurately modifying an image. This typically requires supervised training on labeled paired datasets, which is not always feasible. DualGAN uses 2 opposite GANs to develop an unsupervised learning framework for image-to-image translation that works with unlabeled data. Each of the 2 generated discriminated pairs is responsible for translating an image from one style to the other. In both qualitative and quantitative testing, DualGAN outperforms a traditional GAN, but is in turn outperformed by conditional GANs. This can be observed in the included images, where the GANs are tasked with converting a digital map to its real-life representation and back. Here, GT stands for ground truth, or the expected outcome. Though the results are not perfect, the fact that this algorithm can act unsupervised and on unlabeled data is a very promising start. The next paper is Online Human-Bot Interactions, Detection, Estimation, and Characterization. Increasing evidence suggests that a growing amount of social media traffic is generated by bot accounts. While these bots can be beneficial, there is a growing record of them being used for malicious purposes, such as harassment, propaganda, and fraud. This paper outlines a framework to determine whether or not an active account is a real user or a bot. The algorithm analyzes over 1,000 features of over 5 million tweets to make its binary 0-1 decision. Such features include how filled out a profile is, retweets and mentions, the interval between tweets, and even the tweet length and distribution of parts of speech. The algorithm is fairly successful. Its accuracy rate is comparable to that of the top scorers in the DARPA TwitterBot challenge, which is to say upwards of 90%. However, the algorithm only works on tweets in English, whose grammar conventions are not universal. Further, it is known that social bots are constantly evolving, and the algorithm struggles to detect social bots that it is not explicitly trained on. Despite its language limitations and a lack of future-proofing, this algorithm is still fairly successful. Finally, the star of the show, StackGAN, text-to-photorealistic image synthesis with stacked generative adversarial networks, which is also the paper that I attempted to re-implement. One of the many purposes of GANs is to generate photorealistic images simply from text descriptions. However, these methods have a problem: high resolution. The usual means of increasing image resolution results in nonsensical outputs, such as the one seen in the last row of the image here. This paper and my representation seek to overcome this by dividing the image generation problem into 2 subproblems, each handled by a GAN. The first GAN handles low-resolution image generation. The second GAN takes the results of the first GAN and corrects the defects in the stage before scaling it up to the higher resolution. The base paper's results are very promising. In addition to creating larger images, the images are sharper and more detailed compared to traditional GAN's results. Further, StackGAN achieves higher inception scores than traditional GANs, scoring 3.2 on the Oxford 102 test set compared to the traditional GAN's 2.66. Moving on then to the re-implementation. To reiterate, this is a re-implementation of the StackGAN paper. First, the given text description is turned into a text embedding, then a Gaussian distribution from which the conditioning variable CHAT is sampled from. CHAT is concatenated to a random noise vector that is then fed through several upsampling layers to produce the generated result. Then the result, plus its real counterpart, are downsampled by the discriminator and have the text descriptions embedding concatenated to it. This is fed through one last layer to produce the final real or fake score. The second stage contains a more complex generator, on account of starting with a 64x64 image instead of a random noise vector. Downsampling occurs, followed by an appending of a text embedding. This embedding is different from stage 1's embedding, so the second stage can learn what the first stage omitted. This is then fed through several residual layers. It is here where the model learns the image-to-text relationships. The result is then treated as it was in stage 1, upsampled to an output, then downsampled by the discriminator to make a decision. This re-implementation was generally unsuccessful. The first issue was training time. The re-implementation was afforded just 20 training epochs for stage 1 and 5 for stage 2. The bottleneck was discovered to be data loading. Initially, this resulted in a per epoch training time of 15 hours, later reduced to 3.3. The second issue was that stage 2 was incorrectly implemented. A stopgap fix was implemented, though, as should be expected, the solution resulted in the nonsensical outputs seen to the right. Finally, a third part of the algorithm, meant to apply the trained network to new data, could not be implemented due to it relying on a third-party algorithm that could not be accessed nor replicated. Only stage 1 produced meaningful results. If you squint and tilt your head at the right angle, you can see that stage 1 generator was just beginning to map out the general shapes of the images. The same cannot be said with stage 2 output due to the reasons mentioned above. Moving forward, more work is required on stage 2 and the sampler to get them properly functioning. Stage 1 appears to be functional, but only more training will determine that. Additional experiments on different datasets to produce more qualitative and quantitative results should also be considered. Thank you for your time.